figure out what makes them 0. So -4 here, -1 here, 3 here, 7 here, right? Those are the x-intercepts, 7, 3, -1, -4. And then I look at the powers. Even, odd, even, odd, right? So odd means cross, I cross here, even means bounce, I bounce here, odd means cross, I cross here, even means bounce, I bounce there. So I draw my left side up, my right side up, and then I need to bounce off -4, cross through -1, bounce off 3, come back through and cross through 7. Questions? Sure? Everyone's good? Okay, that's it. So we are, polynomial functions, we're done. The main things, again, that you need to understand is when I give it to you in this form, the left, right, up, down thing is the easy, is the easy part, yeah, because you just look at the degree and leading coefficient. But it's the x-intercepts that suck because then you have to factor. The types of factoring I expect you to be able to do, difference of squares, trinomials, where you have to figure out two numbers that multiply to be something and add up to be the other, and then the grouping. Those are the things. Well, GCF, I forgot. GCF, difference of squares, trinomial thing, and then the grouping. Those are the factoring techniques, and I think you had to do that in all of these. You had to do that, right? This required GCF and difference of squares. This one required GCF, and then the trinomial, the two numbers that multiply to be -4 add up. -12 add up to be 4. This was another one of those, but you had a GCF first. So hopefully with those problems you had some idea of the factoring involved, yeah? Okay, we're going to move on now. I said I was going to start rational functions, but I wanted to take a step back, and it's still polynomial functions, but I want us to go back to quadratic functions. Remember when I told you that all quadratic functions are polynomials? Like every quadratic function is a polynomial. But the way that we go about sketching a quadratic, there was a different set of steps than here. Remember quadratic? We did, quadratics look like this. Quadratic functions was a function f of x equals ax squared plus bx plus c. And then the steps for this were, figure out what A, B, and C are, and then find your vertex. Does it open up or down? Find the vertex, quick sketch. Do you have any x-intercepts? Go find your x-intercepts, go find your y-intercept, draw me the picture, right? That was how we did that. But there's one particular quadratic function, a very special one, that I want to share with you, that I want to talk about, and we're going to do a little experiment here. So first thing, does anyone have, no, here we go. I'll use this. This one, something heavier. There we go, this is pretty heavy. So, index card, there we go. Okay, so this might get loud, so be careful here. Pay attention, I don't want to scare you. So I have a binder here, right? It's kind of heavy. I have this sheet of paper, this little index card, and I'm going to drop them, all right? And I want you to predict which is going to hit the ground first, right? You got your prediction? Yes? Okay, so here we go. 1, 2, 3. It's obvious, yes? So my question is, why did this one hit the ground before this one? Why did this hit before this one hit? Because it's heavier? You all happy with that answer? So this hits the ground because it's heavier than this? So with that logic, what should happen then if I put this piece of paper on top of this and drop them together? If the binder hit first because it's heavier, right, with that idea, then what we should see, tell me if you disagree, is the heavier one start to pull away from the paper, right, and hit the ground, and then this one would follow behind it. If it's because it's heavier. Do you agree with that, or do you all agree with that? You're disagreeing? Now, so you have a different idea? What do you think is going to happen, Garrett? You don't think it's heavier. So let's try this. I would agree that if this one hit the ground first because it's heavier, then what we should see here is the actual pulling away of this from this one, because this one's lighter. Okay, so did y'all see what happened? They went together, didn't they? They dropped exactly the same. Now, I didn't, there's no like tape up here. I didn't, this just, right? You saw me. It's not stuck. So why did they drop together? Well, when I did this initially, right, and dropped them, the reason this one hit the ground first actually has nothing to do with the weight at all. It has nothing to do with the weight. All objects on Earth, okay, will fall at the same rate and hit the ground at the same time if you take air out. If there's no air, then everything should fall together. So the thing that actually slowed this one down was air. Air has a bigger impact on this. It's kind of like if you're driving down the road, I'm sure you've done this at some point in your life, you roll the window down, right, and you put your hand out, right? You do this thing. Come on, everyone's done this, right? Okay, like the air is there, right? It's there. I mean, it's all around us, right? We can feel it when you walk outside. It's real breezy. There's air, right? It can blow buildings over if it's going fast enough. But air just by itself is kind of like water. I mean, it is just very, very thin, right? So the air has a bigger impact on this, and so it slows it down. That's why we use parachutes. Parachutes open up, right, and it captures the air and it slows the person falling down, right? So it doesn't have as much impact on this, all right? So with me putting this on here, what happened was the binder was actually moving the air, right? And the air was not able to get underneath this piece of paper and have the effect that it has when I have them out like this. And so they drop together, all right? So if you drop a feather and a hammer, the hammer hits first because there's air, right? But if you take the air out, the feather and the hammer will drop and hit at the same time. In fact, when we went to the moon, right, back in the 60s, that was one of the first things they did when they got to the moon was they took a hammer and a feather. There's a video of it. You can look it up on YouTube. There's a video of an astronaut standing there, and he drops a feather and a hammer, and they both hit at the same time. And the reason they did it, we knew already that would happen. We knew, but it was kind of like an FU to everyone who doesn't believe science and would say, oh, we have a lot of mystical answers for things, right? At some point we used to think that the Earth was the center of the universe, and so science is always doing that thing. We're like, yeah, told you so, right? So if you take air out, everything falls together. And if things are relatively the same weight, things will fall about the same, right? So if I jump out of a window, right, out of a 30-story building, and I have a rock with me, we're going to hit the ground at the same time. It's a feather and a hammer. That's a huge difference between what happens. But for a lot of objects, the rate's about the same. So because of this, right, we found out that everything on Earth drops at the same rate if you take air out. We said there must be some sort of equation or function that would be able to predict how long it would take for something to hit the ground, right? If air wasn't there and we drop something, can we predict how long it takes? So what I've done here is I've measured with this, and I've never run this experiment in class. This is the first time, so we'll see how this goes. I've measured from the bottom up here. That's 7 feet right there, okay? And what I'm going to do is I'm going to drop a pin from 7 feet, and when I'm going to say ready, set, go. And when I say go, you're going to hit start, and then when you hear it hit, you're going to hit stop. I don't know how this is going to go, all right? And anyone else that wants to time this, you can try. We're going to do it a few times, and then we're going to average what we get, okay? So let's just do a dry run, okay? So I don't know what's going to happen here. So I'm going to say ready, set, go. And when I say go, I'm letting go, all right? Ready, set, go. Were you able to get it? Yeah. Yeah? What did you get? 0.64. 0.64? Okay, let's do it. Let's do it like 5 times, and we're just taking an average. Make sure there's nothing crazy here. Okay. Ready, set, go. 0.50. Okay. Ready, set, go.
0.74.
0.74. Two more. Ready, set, go.
0.71.
0.71, okay. One more. Ready, set, go.
0.87.
0.87, okay, that seems. All right, so let's take the average. I don't have my, you got it? Just add these up. 1, 2, 3, 4. There's 5 of them, divide by 5. What's that? Okay. This is just, you know, when you run experiments like this, you're only as precise as your measurements, right? So we're 0.69? 0.69 seconds is how long it took to drop 7 feet, okay? Now, my question to you now is this. We'll get back to this. I want you to think about this dropping. Let's do it like slow motion. When I first let it go, right? When I let it go, it's not moving initially, right? I let it go and it starts to fall, right? And then what happens? It starts to speed up and speed up and speed up and speed up, right? The longer it's falling, the faster and faster it gets. Do you all understand that? Do you all believe that? Yes, that's not something I have to convince you of. Initially, it's slow, and then it starts to speed up, speed up, speed up. And if there was no floor here, it'd get faster and faster and faster and faster, right? So the distance it travels in the first, like from here to here, that distance takes a certain amount of time, right? Okay, so from here to here, that takes a certain amount of time, right? Let's call that T1. From here to here is T1. That same distance, right, from here to here, T2. This right here, this number should be bigger than this number. In other words, whatever time it took to go from here to here, that same distance shouldn't take as long because now it's moving faster. Make sense? And then that same distance here, this T3, that it should cover that distance even faster than it covered it here, right? So it's speeding up each time. So the question for humans became, can we figure out, is there a function that would tell us exactly where this object would be if I dropped it on Earth if you neglect air, if you take air out of the situation completely? And it turns out we were able to find it, and here it is, all right? I'm going to give you the formula that tells you exactly how objects fall on Earth, okay? Let me write it down first. It's going to look terrible, but I'm going to write it down. D of t equals -16 t squared plus v with a little subscript 0 t plus d with the little subscript 0. All right, so you look at that right now initially and you look at it, you're like, what the, you know, you're like, that looks horrific. All right? But all this is a quadratic function. That's all this is, all right? So let's just see that it's a quadratic function. Instead of using f usually stood for function, right? I'm going to use the letter d. I'm calling this function d, and that stands for distance, okay? This function somehow measures a distance. And instead of using x, I'm going to use t, because t is going to be time, okay? So our variable here is t. So do you all see here, x squared x, and then there's no x's? Here we have t squared t, and then there's no t's, right? And then the rest of it, this number right here, -16, that is a. This v naught right here, that is b. And this d naught right here is our c. So these are just 3 numbers. This number, this number, this number. Now, I just want you to first see that, doesn't that now kind of look like a quadratic? Like kind of? Let me explain what all of these things mean now. Okay, so first let's start with t. T is going to be time, and it's measured in seconds. Okay, it's measured in seconds. In this formula, everywhere you see a t, it's a measurement of time, and it's represented in seconds. What else? Where you see that d with the little subscript, we say that, the way you say that is d naught. D naught. It just, that's just a symbol, or it's a notation we use in physics, all right, d naught. And what this is, and this is real important, this is your starting height. And it's measured in feet. Okay, so for us, in the problem I just did, I dropped an object from 7 feet, didn't I? That would be the d naught for us in this experiment. With me? V naught is your starting speed. Starting speed. Now, I haven't talked about this. This is measured in feet per second. So I want you to think about when I drop that pen, right? When I drop that marker, I just let it go, right? I just let it go. So I did not give it any starting speed. I could have, instead of letting it go, I could have done this. And I could have thrown it down, right? If I threw it down, then I would have been giving it some starting speed. I didn't do that though, right? I could have also done this. Instead of throwing it down, I could have done this. Oh shit. I could have thrown it up, right? And if I throw it up, then it would have to go up a little bit and then come back down. Understand? This V naught helps you determine what happens if you do throw something up or throw it down. All right? So I'm going to add something to this. If up, V naught is a positive number. If down, then V naught is a negative number. And then if you just drop it and you don't do anything, then V naught is 0. And that's what I just did in this experiment. I just let it go. So if you just like let a rock go off a bridge or something, V naught 0. If you throw it up, comes back down, then you've given it some positive V naught. If you throw it down, then you've given it some negative V naught. With me? The next thing I need to explain is what the left side of the equation is. So d of t, the answer, right? The d of t is equal to the height at exactly t seconds. So what this function, remember, the way functions work is you plug a value in and it spits a value out, right? That's the way functions work. Something goes in, something comes out. The way this function works is if you plug in the time, right? You plug in the time, then it will spit out how high it is off the ground now. So if you plug in 1, that would mean 1 second later, this will spit out how high it should be off the ground. Understand? Okay, that is the master formula for all objects dropped, right? Just dropped from some height on Earth. If you take air out. If you want to add air, because it would be important to add air, right? Because we have air, then the formula becomes more complicated, right? And then you have to also not only account for air, you have to account for temperature, you have to account for humidity, a bunch of things. The object you're dropping has properties to it. The more complicated, the more you want it to match the real world, the more complicated this gets. That's why physics is so hard, is because if we start adding in all the true things that impact the situation, these things stop being quadratic and they start being very, very complicated. All right? But this is like the most basic formula. So let's see if we can't model, let's model the experiment we just did, okay? Let's come up with the function that how are we doing here? That we just did. The experiment that we just did, we dropped a pen from 7 feet. First thing I want us to do, let's say part A, I want us to find the quadratic function for this experiment. Okay, that's the first thing I want us to do. Now I erased the master formula, but hopefully you have it written down there. So for us, it'll be, here's the answer, it'll be d of t equals negative 16 t squared. What was our v naught? 0, because we just dropped it. So it would be plus 0t plus, now what was our d naught? What was our starting height measured in feet? 7, right? So 7 feet. We're just going to put 7 here. So we don't need to put this here because it's 0t, it's gone. It's just this. Okay? This right here is the quadratic function that models what we just did. All right? Y'all with me? Now, we dropped it and we measured it 5 times, and we got an average of 0.69 seconds. So what we're saying is that it took 0.69 seconds to go from 7 feet to how many feet? 0, right? Let's see if this is accurate. Let's see if we actually got some good measurements. I'd like for us to try, this is part B, how high is the pen at 0.69 seconds? So what I'm asking you to do here is what? Take 0.69 and do what with it? Plug it in for t, okay? So we want d of 0.69, which means do negative 16 times 0.69 squared plus 7. Get your calculators out if you have one. Let me see, I forgot mine. Oh, there's some up here. I forgot about these. Is there even an on button here? What the hell? Oh, there it is. Okay. So what I'm going to do first here is this, order of operations. I'm going to do 0.69 squared. And when I do that, I get 0.4761 and then plus 7. Now I have to multiply these two together. Ooh, okay. So I get negative 7.6176 plus 7. And if I add those together, I get negative 0.6176. So what do you think about our measurements? What is this telling us? This tells us that after 0.69 seconds, this is how high this pin should have been off the ground, right? Do y'all see it's a negative number? That means that it actually should have already gone like past the ground and down. Does that make sense? So what do you think? 0.69, you think it's actually, that number's too big or too small? A little too big, right? It's a little too big because this actually let it go past the ground. So, but I think it's pretty good. I mean, not bad for like, me just saying go and you start and stopping. I mean, there's always a reaction time involved here, right? So that's the experimental results. What's the true result? How long should it take? That's part C. I'm going to squeeze that in here. For part C, how long should it take to hit the ground? So what am I asking you for here? What am I asking you to do?
Make it equal 0?
Exactly. Remember, this tells us how high we are off the ground, right? And if I'm asking you, how long does it take to hit the ground, then you want to know what's going to make this 0. Because this being 0 means we've hit the ground. So let's go ahead and do that. Let's set negative 16 t squared plus 7 equal to 0. All right? And there's multiple ways to solve this. I'm going to erase this. The way I'm going to do this, I'm going to move the 7 to the other side and make it a negative 7. What do you think I'm going to do now? I'm going to divide both sides by negative 16. I get t squared equals 0.4375. Last step, square root. Okay, I'm going to take the square root on the left side, square root on the right side, so t will be equal to, so you have to do it on your calculator, take the square root. We've had to do that a few times, haven't we? 0. What? 661, okay, we'll just go to that, seconds. So if we had a super precise instrument for doing this, it would have taken us 0.661 seconds. We had one, the first one we did was the closest, right? The very first one, we should have just stuck with that one. And that would have been good, right? Because we would have been real close. But, you know, we tried it a few times. This is the way we do experiments. We do multiple trials, and we take an average. So theoretically, it should take 0.66 seconds for this to occur, all right? On Earth, if we take air out. Okay. All right. Do y'all think you have some slight grasp on how this quadratic function works? Could I ask you to graph this? I could, yes. I could ask you to graph it. Right? Would it open up or down? It would open down, right? Could you find a vertex? Ooh. It's missing, right? Remember it had a 0 here? So isn't B 0? Right? This is A, this is B, this is C. So B would be 0 here. A would be negative 16. So you could find a vertex, couldn't you? You could do a quick sketch. You could find the x-intercepts. You could find the y-intercept, and you could draw it, right? Now, I'm not going to go through the whole process. I'm just going to show you what it would have looked like. Had we drawn this, it would have looked like this. Here's 7. The parabola would have gone like this and like this. And it would have hit here at 0.661. And this would have been actually negative 0.661. Because when you take the square root, you're supposed to do plus or minus. But we don't have negative time. So really, this is what the graph would look like if I just asked you to graph this function and I never told you it was a pen being dropped. If I just said, go graph this, this is what you should get. But because this is a pen being dropped, we would not have this side of the graph because time is only going from 0 to positive, right? We don't have negative time. So that would be the picture. That's the picture of what happens with the pen. Next thing I want to mention is that this works for any planet with gravity, okay? Any planet that has gravity, there is a quadratic function that will tell you how long it takes for something to hit the ground. The only thing that changes if you go to a different planet is this number right here. On Earth, it's negative 16. On the moon, it's about a third of this, but it's still quadratic on the moon. If you go to another planet like Mars, this number changes, but it's still a quadratic, all right? So all objects falling on any planet can be modeled with the quadratic function, okay? All right, I'm going to give you a problem. I want you to do something with this. I'm going to give it to you when we finish up here. But there's one more thing that I want to talk about related to this that I think is interesting, and a lot of people don't know this. So I just want to see what you all think, all right? FYI, off topic. There is another formula, another function called v of t, which is negative 32t plus v naught, okay? That's the same starting speed that we talked about a second ago. This formula right here tells you the speed at which the object would hit the ground. So when I dropped this, right, it was speeding up, speeding up, speeding up. So when it hit the ground, I could tell you how fast it was going when it hit the ground. I could tell you the actual speed of the pen. And all I do is use this formula and replace t with, how long did it take to hit the ground? What was it that we got, like 0.66? If I plug in 0.661 in here, it'll give me the velocity of the pen when it hit the ground. You don't need to know that, I'm just telling you. There's other formulas where you can actually figure out, okay, how long does it take to hit the ground? And then when it hits the ground, how fast is it going? That's the formula for that. Okay, so here's what I want you all to think about now. I'm going to drop 2 pens, right? Drop them exactly the same time. What's going to happen? They're going to hit the ground together or not? Yes, they hit the ground, right? Okay, they hit the ground together. Right? Yeah, we know that. Okay, now, if I take this one and I throw it up a little bit, they're not going to hit the ground at the same time, right? I'm going to drop this one, throw this one up. Right? I mean, we expect that. So if I give one of them some velocity up and the other one I just drop, then they don't hit at the same time. Also, if I just drop this one and this one I throw down, this one's going to get there first, right? Okay, that all I think we can obviously make sense out of. But here's the tricky one. What if I take this one and I drop it, and this one I'm going to throw it that way, just straight out that way? Which one hits the ground first? The one I drop or the one I throw out? Okay, this is hard to do. Let me try and do it this way. I'm gonna throw this one that way at the same time that I drop this one. Okay, you have a prediction as to which is going to hit the ground? I can't do this. What'd you hear? You thought I was going to throw, well, no, I don't want it to hit the wall. But I do want to throw it sideways. So let's do it again. I'll do it from here. I'm going to drop this one and throw this one that way. Which one hits the ground first? What did it sound like to you? Sounded the same? Sound the same? Is that what you thought would happen?
No, but it makes a lot more sense.
It makes sense. So this is an amazing property of objects that are in motion. If I take an object and I just drop it, okay, just let it go, and then I take another object and I throw it sideways and it begins to drop, it'll start, this one will just go straight down, but this one will travel in a path like this, right? And then it'll eventually hit the ground. Here's the ground, right? If I threw this one horizontally, the time it takes to hit the ground is exactly the same as the time it takes for this to hit the ground. Now, if I throw this one up a little bit, then no, it won't happen. If I throw it down a little bit, it won't. But if I throw it completely sideways, like horizontally, they will strike the ground at exactly the same time. What I'm saying is horizontal motion has no impact on how long it takes for something to hit the ground. All right? That's weird. That's a weird concept. If anyone's had some experience with a firearm, okay, a gun, then you may notice that so what I'm trying to tell you is if this was a bullet, right? If I was holding a bullet in my hand and this one was a bullet loaded into a rifle and I dropped this one and I fired the rifle at exactly the same